Boron trifluoride. You should have that memorized by now. Shh. Please. Boron trifluoride. He usually comes in about 3 or 4 minutes. Yep. All right, boron trifluoride. You should be told by now that that's the exception the AP test will almost always use, right? There's no double bond. Even if it did double bond, you could still get this question right. So it says has 3 bonding domains. That is true. 1, 2, 3. And its electron domain geometry is trigonal planar. That is a true statement because there's not an extra pair of electrons on the boron. Right? So that is true. Electron domains for single bonds exert greater force on adjacent domains than electron domains for multiple bonds. This is false. All right? This was a slide years before. Getting closer, I went past it. Non-bonding pairs are physically larger, therefore they exert more force. And then double and triple bonds place greater electron density on one side of the central atom than do single bonds, therefore they also affect bond angles. So a double bond will push farther or occupy more space than a single bond will. You okay with that? This electron density, it sort of should make sense. There's 4 pairs of electrons hanging out here, so they're going to occupy more space than just 2 pairs of electrons. So they will force the other ones away. The statement in the true-false was written opposite, so that's why it's false. The double bond will still occupy more space. Wow, where am I? There we go. All right, electrons in core orbitals contribute to atomic bonding. I would hope that you knew that from multiple chapters. Electron domain structure always matches the molecular structure. That is false as well, correct? If it did, this class would be a little bit easier. That'd be nice. But the reason why it won't, by the way, remember, these do not match if there's at least one non-bonding pair of electrons. You can have more than one, but if there's even one at all, there it's going to be different. All right, and then SO3 is a polar substance. So this one has to do with what we did the last few seconds yesterday. If you remember, we've drawn SO3 a few times. It ends up looking like this. Okay. And each individual bond itself is polar. Now, to answer this question, you don't actually have to know that. But between S and O, it is a polar bond. But what we talked about yesterday is that since this is trigonal planar, the electron moves that way, and that way. And if you add those all up, they cancel out. And you have no dipole moment. A dipole moment is a weird term, but what that means is you have no movement of the electron from one side or the other. Are you okay with that? So we would say SO3 is nonpolar, even though it consists of bonds, which are polar. So is SO3, right, SO3 is polar is a false statement. Are you okay with that explanation? Okay, there's one more here that we couldn't answer until after today's lecture. Okay. What now I would like you to do, I want you to draw a grid. It doesn't need to be big at all. So let's see. I'm looking for insert table. Okay. It's already that way because I just made one the same size. All right, just put this in your notes. It's 5 by 3. I think it better be. Yep. Now, this box is for you, so like if you want to just put initials for things, that's fine. What we're going to do, we're going to try and see what we got from yesterday. From our memory. You with me? From your memory. Try not to use your notes here. So, what you're going to do, label as many of these as possible without using your notes. I'm looking for the name of the shape once again. Same as yesterday, you're just going to glance up and now you would just write the name in the grid of your box. So linear, we all right with that? Linear, bent. Anyone have the first column perfect? Raise your hands. Okay. I'd give Benson a 5, but she's toxic. All right. This is the weird one that's sideways, but if it wasn't sideways, it'd look like a what? All right. Seesaw. This one we've done 10 times. It would be trigonal planar. All right. What's this one? Octahedral. All right. What do we call this one? Linear. Leonard. Whatever. We're good. We're good. What do we call this one? Bent. What do we call this one? Trigonal bipyramidal. All right. Up here, this is what we didn't have to do. What was it anyway? Pentagonal bipyramidal. Yeah. Pretty weird, huh? The reason we don't do this is because this very much expands the D shell, which is still in debate if that's actually how it works, even here in 2018. So, whatever. What do we call this? Tetra. What do we call this? Trigonal pyramidal. And then we're up to the top right. That is square pyramidal. Right? What do we have here? Square. And what do we have here? Tom-shaped. Actually, if it was Tom-shaped, it'd be like a dude with a really fat belly.
Mine is just, well, I got wrong.
Yep, I'm pretty fat. Actually, I've lost 7 pounds in a week, so whatever. I'm a pig. All right, we left off on this slide. And we ended on this picture. Tetra, whatever. Tetrahedral almost always makes non-polar substances like this. The reason why is because it's symmetrical. All right? The dipole moments, which are these little arrows with plus signs on them, they typically will cancel themselves out in things that are symmetrical, meaning things that are typically planar, or this tetrahedral, or square planar. But this one is polar. If you remember, I talked about this right at the very end. We said it's polar because this one has a different molecule on top, and we should know chlorine is very electronegative, right? So, the overall dipole moment here won't be super big because there is an attraction here, here, and here. Not much. All right? But this one here will win. Okay? So when you're asked if it's polar or not, looking at the shape is the first thing you should do. All right? And if it looks like something that can cancel everything out, you say nonpolar, but also double check that all the atoms match around the central atom. It's sort of a trick question. Are we okay with that? Okay. So to review polarity, if it's just 2 atoms and one's more electronegative, it's always polar. All right? Planar substances are typically nonpolar as long as all the atoms match. All right? Things that are pyramidal are typically polar, as long as their bonds are, because there's a whole thing to like cancel it out. Okay? Now these are exception to everything, but you don't need to know the minute exceptions here. And then typically if something has more than just two types of atoms, you got to be really careful and check. All right, do I know if this is more polar than that? You should know O, F, and Cl are gigantically polar compared to everyone else. Are we okay with that? Right. Thank you. All right. Now, there's not a ton on the test about this. In fact, you already have seen the only question on polarity on the whole test, if I remember right. But it is something you should store away in your recall memory area if you have one. All right. We have two things left. They are hybrid orbitals. They're super non-math. No. Chill. Like, I am going to ask you to memorize something, but it's as easy, it's way easier than anything we've done so far this whole chapter. All right, so we think of covalent bonds forming through the sharing of electrons by adjacent atoms. In such approach, this can only occur when orbitals of the two atoms literally overlap. All right? So we've talked about them bonding before, but we never maybe have said why. All right? So what we mean by overlap is literally this, if you'll look at the screen for a second. We can have a molecule called hydrogen fluoride. The reason we can is because hydrogen has 1 electron that it will share. Fluorine has 9 total electrons, but desperately wants 10. Are you okay with that? All right, and we know that these react and the electron is shared. So what literally happens is the 1s orbital will overlap with this 2p orbital. And now hydrogen, which is occupying this space here, all right, it feels like it has its 2 valence electrons. Are you okay with that? And then fluorine's valence would be all 8 right here, and it feels like it has a full octet. Who's okay with that so far? All right, the 1s and the p literally overlap, and they're going to form what we call hybrid orbitals. The term hybrid is easier to understand than ever because it's used in cars. A hybrid is something that uses gas and typically electric, right? Meaning it's a mixture of 2 types of things. This orbital right here is a hybrid orbital. Look at the screen for 10 seconds. It's a hybrid orbital of an S, and what was this one representing? A P, right? So we would say HF has SP hybridization, meaning an S and a P overlap. Is that the worst thing we've done so far? Okay. Now, nitrogen is diatomic. We know that, correct? All right, so nitrogen here, this is just flipped, but it's the same thing. Nitrogen will just overlap with another nitrogen, and they form a bond. How cool is that? If we were to draw the nitrogen molecule, do you remember it had a triple bond? It did, right? And you can see that triple bond represented when these 3 orbitals overlap.
It just works.
It just works. It's okay. Then, who's heard of NH3? We've drawn it like 5 times, right? Well, NH3 works because N needs to overlap with hydrogen 3 separate times. Oh, I didn't realize the S was coming, so it's going to be ugly, but you get the picture. They just overlap, and now life's great. Okay? So this is what we call overlap, and where bonding is concerned, we call it overlap bonding. We call these hybrid orbitals. Now, once you know the electron domain geometry, you know the hybridization state of the atom. Now this, do not even remotely draw everything on this slide. But this is how it works. And it's pretty simple because we just follow a pattern. When we talk about like overlap, we have the S, we have the 2S, 2P, and we've always been saying this could hold 2, this could hold 2, and these could hold 6, right? But when we talk about overlap, if they're going to overlap, they only had 1 before. You with me? There's only 1. So now when we do this process, we're going to say that you can have an S, and only one of them, and you can have 3 P's. Because there's an S box and 3 P boxes that can overlap. Okay? Then we put, instead of putting PP, the SP, if we were using all 4 of these hybrid orbitals. So coming back here, if you have your 2 or your linear, so you have one on one side and one on the other, all right, we have an SP, one from the S and one from the P. If we have something that has 3, we now have SP2. Remember, S has a 1, and it will always add to whatever my electron domain geometry is. Okay, if my electron domain geometry is 4 or tetrahedral, I have an S and then all 3 P's involved, because that's how I add to 4. If I have 5, all right, then I have an S. How come I'm never putting 2 in an S? Because that's not how it works. We're now talking about the ability to overlap. And when you overlap, you have 1 from one and 1 from the other. So we just count it as 1. So it's half the number we're used to. So this is 5. We have 1 in the S, 3 P's overlap, and 1 D overlap. All right? And then, lastly, if we have 6, we have SP3D2, because this always at the top will add to 6. The hybridization will always add to the electron domain number. Okay? So if we come back to any example we did before, we can find out the hybridization of these things. So we don't do it like, well, we can. This one, well, we typically don't do it when it's just one atom to one atom, so don't stress much about that. So let's look here. How many electron domains do we have here? We have 4. To get 4, that would require an S to overlap, and that's one of them. We need 3 more, so I put my P, and we have all 3 of those. We okay with that? Carbon looks like this. Typically, carbon has 1, 2, 3, 4, 5, 6. But when it starts, the first energy that goes in, it promotes one of the 2 up to here. And now look, carbon will form a bond with 1 S and 3 P boxes. That. All right. Now, this gets tricky because there is a pair of electrons right here. How do we know that? All right, it's bent away for some reason, or it's pyramidal, right? So what are the electron domains here? 1, 2, 3, 4, right? So what would we call this? Tetrahedral, or it's 4, so it's sp3 again. Okay? This is a little trickier, but it's fine. What do we have here when it's just 3? sp2. Okay? So yeah, it's another layer on the onion, but the hard part was already done. If we know the electron domains, we can find the molecular geometry. That one was a little hard, but if we know the electron domains, we can also find the hybridization of the central atom just by making sure that things add up to equal the number of electron domains. You okay with that? Okay, I think this last true-false that we couldn't do, I think it was on one of these. Let me clear all this crap and then uncover it. Oh, well, I thought it was more technical. This is just pretty much a definition. Hybridization is the process of mixing atomic orbitals as atoms approach each other to form a bond. That is true. All right, there is another question on the test somewhere. It's probably, I saved 1 or 2 for tomorrow to start, where it says something, something, something is like sp3 hybridized or something like that. You just count the electron domains, and if it adds up, then the answer is yes. If not, it's not. All right, let's come back. That was not the hardest thing so far, right? Okay. All right. So, to summarize, use your Lewis structure to determine the electron domain geometry. Then remember you can only have 1 s, 3 p, and 5 ds. We're talking about the orbitals or the squares that can overlap now. The hybrid orbital notation will always add to equal the number of electron domains. All right. So then there's 3 examples. CH4 had 4 electron domains. It overlaps SPPP or SP3. BF3, 3, so it has SPP or SP2. PCl6, 6 electron domains, SPPP, DD. And that's the highest we go. Okay? All right. I'll pause that. I see a bunch of... oh, here's 3 practice ones. Do you want to do these? All right. What time we got? 30. Oh, yeah, we have plenty. All right. So hopefully this was fine. Hybridization here, there are 2 electron domains around carbon, correct? So 2 would be 1s and 1p. So sp. This has 3. There's a double bond between the O because you have to octet carbon. So you end up with 3. So that is just sp2. All right, 1, 2, 3 here as well. So if there's 3, we just did it again. It was sp2. Fair enough? Okay, I'm not picking on Emily, but she's even pumped about this, right? And usually she doesn't love when I drop a new whole thing. Okay, all this stuff up here is going to say what I just said, so I'm just going to skip through that. Are you okay with that? Okay, now, don't write any of these notes until I tell you to. This is an extremely minute thing, but there is one part of it that's important. So, hybridization, so valence bond theory, all right, and there's books about valence bond theory, but we need to know basically 2 little nuggets. So hybridization is a major player in this approach to bonding. There are 2 ways orbitals can overlap to form bonds between atoms. Okay, so we just said, hey, one orbital comes along and it overlaps another orbital. So all we're saying in valence bond theory is there's 2 ways they can align themselves. And they really are very easy to understand if you just think of them in terms of a fist bump versus a handshake. So what you do need to know is this thing called a sigma bond. And sigma is this symbol right here. All right, it's like a little O with a little top on it. That's a sigma. And that is what we call head-to-head overlap. So it's where the tips, essentially, they overlap each other to share that electron. All right? This is the fist bump. You'll see why the handshake is the handshake in a second. All right? So, sigma is like a fist bump where the tips overlap each other. Now, pi is where the sides of the P clouds overlap each other. So there's way more contact. Like a handshake, there's way more physical contact with whoever you're talking to. So like right now, we all can hear Emily's sick. If I was going to be like, what's up? I wouldn't shake her hand, right? I'd maybe give her a fist bump. I don't want whatever she's had. She's had it for a month. Okay? So this is where the P clouds overlap. They align in two separate locations, and they're significantly more energetic. You don't need this electron density, by the way. Just need to know it's side-to-side overlap. Okay. Now, the most important thing you need to know is the following. Single bonds are always sigma. Now that's convenient because they both start with S. Single bonds are sigma bonds because sigma overlap is greater, resulting in stronger bond and more energy lowering. I guess I just lied about something, but don't call me on it, Isaac. What's that? Sorry. All right, now, a double bond, or in a multiple bond, one of the two, or three, is a sigma bond, and the rest are pi bonds. So, since you have two bonds here now, you have one sigma, one pi. You always have at least one sigma, and the rest would be pi bonds. We don't talk about quadruple bonds here, but we can just for a second. One sigma, three pi bonds. You okay with that? You'll never have more than one sigma bond in the same bond. Like that. See why I didn't try and draw it? These pictures are in your book. And don't draw these. We're not even going to go to these slides typically. Okay, but that's how they line up. They make these pretty complicated shapes here. All right, this one would obviously have no double bonds. That'd be all single bonds. The way you would know that is there's no red to red overlap. All right, here there is the red lining up with the red right there. Okay, now, to summarize. Go ahead. Yes. Every single bond is a sigma bond. And then a double, you would add another pi with it. Triple, you'd add another 2 pi. So here we go. To summarize, a single bond is always a sigma bond. A double bond is always a sigma and a pi bond. A triple bond is always a sigma and 2 pi bonds. All right? So here's the practice question. How many sigma and how many pi in C3H6? So to do it, you draw it, count up bonds, and use the rules above. So we got, that won't take too long. Please remember, if this number right here is only 2x of what C is, there is a double bond involved. try and draw that. So the next thing we would do is count the number of total bonds. 1, 2, 3, 4, 5, 6, 7, 8. So I know I have 8 sigma bonds, right? The next thing to do, is there any double or triple bonds? Yes, there's one double bond, which means I have at least, well, not at least, I have one pi bond. Are we okay with that? It's just 8 and 1. So we added 2 things today, but neither one of them are independently that difficult, I hope. And together, if you think about it, I mean, now the way that I test, and I test the way the AP test does, we have one stem that we can ask like 10 questions about, right? And we will. So, practice test review Monday, that would be from last year. There is a practice test on the internet. All right, we will review tomorrow, and we will test on Thursday. I don't know. We're fine. Like from 3 years ago, we're behind. From last year, we are right where we need to be, because Chapter 10, they had an assignment for Chapter 10 over Christmas break, and that's coming up.
Is it a big assignment or is it like a...
It's Ed puzzles.